Hi everybody, and welcome back. Continuing with chapter 11 on uniform circular motion, we've talked about so far the idea of a centripetal acceleration. That is, that there is an acceleration that is changing the velocity of an object such that it moves in a circle. It doesn't necessarily change the magnitude of the velocity, but it changes the direction of the velocity, and whether it's a magnitude or direction change, it's still a change, and so you have to have an acceleration for that. So that is a centripetal acceleration. Today we're going to bring the idea of force into that, and we're actually going to go back to Newton's second law, which should look pretty familiar to you. F is equal to ma. Well, we have some kind of special varieties of that. F, and this R is for radial force, but I'm going to just call it F sub c. That is for centripetal force, all right? Just to stay consistent with the centripetal acceleration as well. So the centripetal force equals mass times the centripetal acceleration, and I usually just call that c as well, all right? But this is the force that is directed towards the center. If you have an object moving in a circle, all right, it's moving in a circle because, first of all, there is an acceleration directed towards the center. That's the centripetal acceleration that we talked about. And if that object that is moving has a mass, it's a solid object, all right, then it requires some force in order to make that mass have that acceleration. All right, so the centripetal force is really what is felt directed towards the center. I'm going to call that Fc. All right, and we talked about a couple different ways that you can notate the centripetal acceleration, and when we do some examples, I'll kind of review them as well. We said that centripetal acceleration is, we said it's v squared over r. All right, we also said that it's also equal to 4 pi squared r over t squared, or period squared, time period squared. It's also equal to 4 pi squared r f squared, and f being frequency, and frequency and time and period are basically inverses of each other, so that's why you can have basically the same thing right there. But wherever we have centripetal acceleration, we can substitute in any one of these values that deal with the speed, how fast is the object moving, what's the radius of the circle, how long does it take to go around, and so forth. So any other condition other than a centripetal force being applied toward the center, and the object will not move in a circle, in a circular path. So the assumption is that all objects are going to move in circular paths, all because of this centripetal force caused by the mass feeling that centripetal acceleration. Now, centripetal sounds an awful lot like a word that you've probably heard before, and that is centrifugal force. If, let's say you are in a and we're going to talk about this a little bit later on, but there is an amusement park ride where if you look down on it from the top, it's kind of like a cylinder, and you get inside of it. So here's you, all right, looking down on you from the top, and the cylinder starts to spin. All right, it starts to spin, we'll say counterclockwise like that. I think it's called either the gravitron or the rotor sometimes, but this thing spins around, and you feel like you are forced to the wall. Right? You feel like you're stuck against the wall. In some cases, the floor drops down and you get stuck to the wall, that kind of thing, but you're spinning around. Nothing is really forcing you to the outside. This force, the centrifugal or center fleeing force, by the way, fugal is the same word that fugitive has it, and fugitives tend to flee. So this force that moves away from the center, centrifugal, it really isn't there. What's happening is that you have a tendency, I'll draw this in green actually, you have a tendency to want to move in a straight line, like that. That's your velocity at any one point. Well, the fact that you're inside a curved cylinder, it's preventing you from moving in that straight line, so it's like the cylinder is kind of correcting you into that circle. Your tendency to want to move in a straight line makes you feel pressed against the outside. But really what the cylinder is doing is, let's say the cylinder all of a sudden wasn't there. That is, this circular wall you're inside. What would happen? Well, you'd fly out into the parking lot, right? What the cylinder is really doing is it is applying a force towards the center to actually keep you in that circle, to keep you inside that circular path. If the walls were made of paper, that probably wouldn't do a very good job of applying a centripetal force, and you'd break through it and fly in a straight line out into the parking lot. Well, the fact that the wall, or that cylinder wall, is applying that force to you towards the center makes you feel pushed to the outside. But there really is no force moving to the outside. It's really the centripetal force directed towards the center that makes you feel pushed to the outside. The same thing is true of when your car goes around a corner. All right, there's your car right there. You have a tendency to want to move in a straight line like that. The car is correcting you and keeping you inside a curved line, so you feel pushed to the outside of the car. Same thing with the gravitron or rotor thing right here. All right, so we'll do a quick example or two, actually a couple of conceptual examples, and then we'll do an actual example where we do some calculations. Incidentally, I should point out, I think my example numbers are a little bit off, so this should be example number 3, 11.3 right here, and that's not even a very good 3. All right, but this is, there we go, okay? So we've got a puck attached to a table, and there's a hole in the table, and there's probably some sort of tension on this string right here, and it's causing the puck to swing around like this. Well, at this point, the string breaks, all right? And the question is, what direction is the puck going to want to move? Is it going to want to move straight to the outside, or any one of these other paths as well? Well, remember, just a second ago, we said the centripetal force is a force that is being applied towards the center to keep you in that circular path. All right? Otherwise, if that force weren't there, what direction would you want to go? Well, this green arrow kind of tells the story. You want to go in a kind of in a tangent path. So at this point, there's no more centripetal acceleration, therefore no centripetal force. So whatever the tangent path is, right at that point that you happen to be going at, that's the path you'll take. You're not going to move in a curved path that way or this way right here. Those aren't right. You're going to move in a straight path. There's no more centripetal force, so therefore your last known tangential velocity is going to be the velocity that your puck actually takes. All right, so it's going to move off in a straight line just like that. All right? So no calculations right there, but just sort of a thought that at any one point, that circularly moving object wants to move off in a straight line if there's no center-seeking force pulling it back into that circle. All right, here's another kind of a thought experiment right here. Let me draw kind of a circular track, and I'm getting better at my circles. There we go. Yeah, that's not too good. No, that's all right. So here's our car right here. I'll draw it in 2 spots right here, so it's going that way and this way, okay? So from above, that's our red car. The car is being driven with a constant speed around a circular track. All right, we say constant speed. Couldn't we say constant velocity? Could we say constant velocity? Yes or no? Well, remember that velocity is a vector, all right? And that means that it has a magnitude and a direction. So it can have a constant magnitude, but does this car have a constant direction? Not given these 2 points right here, it doesn't. Here's the velocity at one point, the direction, and here's the direction at another point. So clearly, the velocity is not the same because the direction keeps changing. The magnitude can be the same, but if the direction changes, you have a different velocity. So no, it's not a constant velocity. Is it speed constant? Ask yourself this. First of all, is speed a vector? No, it's a scalar quantity, which is just an amount, so it's not direction dependent. So, can you go around a circular track and look at your speedometer and have it read the same thing? Sure, absolutely. You can. That's why it's called a speedometer, not a velocityometer, because as soon as you change direction, the velocity technically changes. All right? So, our acceleration. There's something creating an acceleration towards the center right here. Centripetal acceleration, centripetal acceleration. All right, is the magnitude of the acceleration constant? Magnitude simply means the amount. Now, acceleration is a vector, yes. It has magnitude and direction, but this is just asking about the magnitude. Is the magnitude constant? Yeah, it sure is. You've got a certain mass right here. You have a perfectly, try to imagine that perfectly circular circle, all right? And that acceleration from all different angles that it's acting on the car that direction, this direction, and every angle in between is keeping that car in a perfect circle. So yes, that magnitude of the acceleration is constant. Is the direction constant? Well, one look at that diagram right there, and you can say absolutely not. All right, the direction of the acceleration keeps constantly changing. That's why whenever you whip something around over your head, you're pulling, like say something on the end of a string, or like a yo-yo or something like that. You keep pulling towards the inside, and your hand has to wiggle back and forth a little bit because you keep constantly changing the direction that you're accelerating that yo-yo or whatever that string is on the that object is on the end of your string. So we've got no, yes, yes, and no. All right, just something to think about. All right, so this last example, this next example, oh, by the way, let me go back here. This should be 4. All right, that's a pretty lame 4 there. All right, and the next example we're going to do is going to be example 11.5, and it's going to be actually have some values. All right. Well, let's talk real quickly though about horizontal uniform circular motion problems. All right. First of all, when you do these problems, I want you to draw a free body diagram. All right. Just like the one that we did. It doesn't need to be a piece of art. It just needs to show the object moving in a circle. And in many cases, I kind of kill 2 birds with 1 stone by usually drawing the circle overhead at sort of an angle. So you can see it sort of from the side, but also from top as well. So that's sort of like an oblique view. Obviously, it's not a real circle. It's kind of an ellipse. But if you draw an ellipse, you can show it from two different angles. So remember, the radial direction, that is delta r, or I'm sorry, or r hat, I should say, with a little upside down V over top of it. That direction towards the center is positive. Towards the outside is negative. And I thought I had a typo on that at some point. But anyway, if I see that, I'll correct it. But yes, towards the center is positive. All right. So what is going to be acting towards the center? It could be a string. And so label your tension forces. It may possibly be that there's friction acting towards the center, keeping your object in a circular path. Maybe it's a normal force that is doing that. So we're going to label all of those forces that are directed towards the center. Towards the center is positive, towards the outside is negative. All right. Write an equation, write a general equation that satisfies a condition for net force in the centripetal force, I should say, equals mass times centripetal acceleration. All right. So sum up all the forces that are acting on this object to keep it in the path, and then set it equal to ma, just like we've done before. We always said the net force, kind of a global equation for it is simply ma, right? And then we also said the net force on an object in the past is the sum of all the forces on it. Force 1 plus force 2 minus force 3, etc. All right. Well, this is just kind of another version of that. Instead of ma, we're going to have, well, instead of force, we're going to have centripetal force, and instead of ma, we're going to have mass times the centripetal acceleration. All right. So write all your equations with regards to that. And in some cases, we'll have to apply some other sort of condition. That is, we might say that the force that is acting towards the center is up to a certain amount. That is, like this friction force right here. All right. Well, if the force required to keep something in the circle is greater than the friction force, then it won't stay in the circle. So there's little conditions that we may need to apply, but we'll talk about those when we get onto them. All right. The two big things is draw your free body diagram and write everything with respect to ma. And that centripetal force is ma. All right. Let's do this next example right here, and this will be it for this segment of the video. Once again, this is incorrectly labeled. I'm going to call this 11.5. Again, for the next few, all of these are going to be the wrong number because I had some numbering problems. 11.5, and I'm going to take all this and shrink it down a little bit because we're going to need this space here. Okay, so we'll do that. We've got a car moving around a curve, a 1,200 kilogram car moving around a curve. So let's go ahead and write down what we know. Mass equals 1,200 kilograms. Around a corner with a radius 45 meters. All right, so that's our R, 45 meters. That's a good start. Okay. We've got a coefficient of static friction. No, not kinetic friction. The tires are not sliding, but they're maintaining contact with the road and not sliding. So we'd call that static friction. So that's 0.82. And by the way, that's a good thing. That's a good high decimal because you want grippiness between your tires and the road. All right, the question is, what is the maximum speed that the car can go around that curve with, all right, without skidding? So here's one of those conditions right here where we want to know the maximum speed. So what we're going to simply do is just solve for whatever the speed is that it would be at if, by setting it equal to the required centripetal acceleration, that would keep that car in the path right there. All right, I think it'll make sense as we do it. All right, now let's look at this car for a second. I'm going to draw the car again, actually. I already used blue, but I'll use light blue. All right, so here's our car, and it's going to be pointing right at us, okay? Okay, and there is the road. So, what is keeping it, and the road, by the way, is curving like that, all right? What is keeping that car on the curve? Well, there's no string attached to the middle of the road, right? There's no rod or anything. There's no wall keeping the car in. The only thing keeping the car on the road is, in fact, friction. Friction. Static friction. All right, so I'm going to label that as green right there, all right? The friction between the wheels and the road, the static friction, is the only thing keeping that car there. And so, if we can solve for the static friction, we can really say that the static friction is equal to the net centripetal force keeping that car in that circular path right there. Okay, so static friction. Well, we have an equation for that, right? Static friction. That is our coefficient of static friction times m times g or mg. Mg being, I'll draw that in red, mg being our weight force, right? And really we say it's mg because that mg has to be equal and opposite to the normal force. All right, so really, actually in the past we said the static friction force is mu s times the normal force. Well, the normal force is mg, and so that's why we have that right there. Okay, now I'm not going to calculate this out quite just yet. We don't need to quite just yet, but we can say that this force right here, the static friction force, is the net centripetal force acting towards the center. There is no other centripetal force acting towards the center right there. All right. Well, what's the other way we can state net centripetal force? That's mass times centripetal acceleration, right? So these two things being equal, I should have written that on the other side, but that's all right. We can say, all right, well, the static friction force equals mass times centripetal acceleration, like that. Well, let's expand these out a little bit. All right, we said our static friction force is mu s times mg. That looks like a minus sign, doesn't it? Sorry about that. Times mg equals, it still looks like a minus sign, but that's all right. You know it's not. You know it's a times sign. Equals mass times centripetal acceleration. Okay, let's ask ourselves now, what are we solving for? How do we want to restate that centripetal acceleration so that we can get what we're solving for? Well, we're solving for a velocity, all right, a maximum velocity. This car will stay on the road if there is any acceleration less than this. Oops, I don't want to do that. But the maximum velocity is the velocity that it will stay at that it needs to stay at if you need all this available centripetal acceleration right here. All right, so what's one way we can state centripetal acceleration with respect to velocity? Well, the first way we did it, that was v squared over r. Okay, so this is our net force, our static friction force. This is our mass. This is our acceleration right here. And I think you will see something that will come in handy later on. It really doesn't matter what the mass of this car is, because you're going to see these masses cancel out. In many cases, the mass matters, but in this case, where the force directed towards the center is a function of the mass of the car, and the centripetal acceleration is a function of the mass of the car, those masses cancel out. So let's just go ahead and solve for our velocity right here, and then we'll plug in what we need to know, or what we know, and we'll solve for it. Okay? I keep changing colors here. That's not right. We'll just stay with green. All right, so I'm going to bring the r up to the other side, so we can say v squared equals r times coefficient of static friction times g. And so therefore v has to be the square root of all that. R us, or mu s times g. All right, now let's plug in, and we can solve for the velocity, the maximum velocity that will that the car can have. So our r is 45 meters. Our mu s, or coefficient of static friction, is 0.82. And g, of course, is 9.81 meters per second squared. All right, multiply them together, take the square root. What do we get? And I get the velocity, or the maximum velocity, equals 19.0 meters per second. That's our final answer right there. All right, now it can go slower than this. It can certainly go slower than this, and the car will still stay on the track because there's more than enough coefficient of, there's more than enough static friction force to keep it in the track. But this right here is the maximum amount of velocity that will completely max out the available friction and still keep the car on the track. All right, so we did a couple of examples right there. Thanks for following along. That was 3 of them, I think. Example 3, example 4, and example 5. Thanks for following along. I'll see you on the next one.